All right. Um, well, welcome everybody. Hopefully you can hear me. I appear to be unmuted. Um, my name is Rick Feinberg. I am the AAS press officer, and it is my distinct pleasure to welcome all of you to the very first virtual press conference that we've ever put on at a AAS meeting, because we're not in Wisconsin like we thought we'd be. So you see a rogues gallery here on the screen, I think, if you're seeing my gallery view. I don't know if everybody's in the same position all the time, so let me introduce my two assistants. Tharani Konchadi is our AAS Media Fellow. She will be helping today, as will Susanna Kohler, who is the editor of our AAS Nova website. The subject of today's press conference is Galaxies, Weird and Wonderful. And we have four really great presentations to look forward to. Before I introduce the panelists and say anything else about the subject, I just wanted to mention that there is at least one press release going out this morning, and I think there might be one or two more coming a little bit later. If you have a question during the briefing, you should use the Q&A feature that you'll find at the bottom of your Zoom screen. And you can type your question in there and make sure that you indicate who it is that you're asking the question of. And if you can, please give your affiliation as well. I think we can see your names. Yeah, I see your names, but I don't see any affiliations. So it would be great if you could, type your question, start with, science news question for whoever, and then type your question. Attendees are able to comment on other people's questions, which means you can, if you think you know the answer, you can answer it. But you can also do something called upvoting, I think. As panelists, we don't have the same controls that the regular attendees do, but I think you can upvote questions. So if you see a question that was the same question you were going to ask, you can upvote it, and that tells us that it's a higher priority question because there's more than one person who wants to ask it. If we recognize journalists, we will give them priority in asking questions. But if you're not a journalist, if you're a regular meeting attendee or a student or a presenter from in another briefing, feel free to ask a question as well. Okay, so the way our press conferences work, and we're going to do it the same here as we would if we were in Madison, is we have all the speakers speak in order, and then we go to questions and answers. But that doesn't mean you can't start typing questions into the Q&A box as we're going along. It's just that we like to hold the Q&A to the end to make sure that all of the speakers get their allotted time. Okay, so for those of you who've been to AAS briefings before, you know that I like to organize them thematically. And so this morning's briefing is called Galaxies, Weird and Wonderful. And we're going to hear some results on some interesting individual galaxies. And we're also going to hear some results of what looks to be kind of strange behavior on the part of galaxies as a group. So the four speakers that we have this morning, we'll begin with Teresa Brainerd. She's at Boston University. She also happens to be on the board of trustees of the AAS. Her topic is lopsided satellite distributions around isolated host galaxies. She'll be followed by Lior Shamir from Kansas State University. His topic is galaxy spin directions show large-scale asymmetries and redshift dependence. Next, we'll hear from Shanskriti Das from Ohio State University. The title of her presentation is Evidence for a Massive Hot Circumgalactic Medium Enveloping a Large Luminous Galaxy. And last but not least, Ripan Saha from the University of Missouri at Kansas City, a proto-supercluster of galaxies at high redshift. So with that, I'm going to turn it over to Teresa. The rest of us are going to mute ourselves and stop our video to give Teresa the spotlight. And I apologize in advance if we run into any kinds of technical difficulties, but hopefully we won't. And we'll go from here.
Okay. All right. Thank you very much, Rick, and hello, everyone. I'd like to start by acknowledging the contributions of my collaborator, Adam Samuels. Adam is a first-year grad student, and he's responsible for the vast majority of the hard work that led to the exciting results I'm going to share with you today. The motivation for our work is a test of one of the predictions of the cold dark matter theory. Most astronomers agree that about 85% of the mass of the universe is in the form of some kind of invisible dark matter. And the most successful model for the dark matter is cold dark matter, or CDM. CDM predicts that all large galaxies live at the centers of enormous invisible halos of dark matter. And the image on the screen is meant to illustrate this concept. What's important for our work is that CDM predicts the halos of galaxies are not spherical. Instead, the halos are somewhat flattened, and if you could actually see them, you'd expect the halos to appear elliptical on the sky. We wanted to see if we could find a way to determine whether the halos of large isolated galaxies were flattened or not. By isolated, what I mean is that each of our large central galaxies has no other similarly large galaxies anywhere nearby. Almost all large galaxies are surrounded by smaller, fainter galaxies known as satellite galaxies. The image on the screen shows you what we expected to see when we looked at the locations of satellite galaxies relative to the larger central galaxies. We call the large central galaxies, these guys here, we call them host galaxies. And we expected to see their satellites distributed all around them with roughly elliptical symmetry. That is, we expected the satellites to fill up the dark matter halos of their host galaxies with the same sort of elliptical symmetry. And because of this symmetry, we expected there would be the same number of satellites on one side of the host galaxy as there were on the opposite side. Now, studies of the locations of satellite galaxies are by no means new. What's new about our study is that our host satellite systems have between 5 and 26 satellites each, whereas previous studies typically only had 1 or 2 satellites per system. Why that's important is that ours is the first study in which we can look systematically at how the satellites are distributed inside each individual host satellite system. When we started looking at our systems in detail, we found something we weren't expecting. And this slide shows a particularly remarkable example of what we found. This slide shows a spiral host galaxy known as NGC 2998 and its 17 satellites. NGC 2998 is marked by the blue circle, and the satellites are marked by all of the yellow circles you can see around the sky. What's really clear is that the satellite distribution is not centered on the host galaxy. 16 of these 17 satellites are over to the east side of NGC 2998. Over here on the west is the one lone satellite on the western side of the host. So rather than elliptical symmetry, the satellite galaxy locations are showing a lopsided distribution relative to the location of the host. We developed a simple statistic to measure the lopsidedness of the satellite locations, which effectively comes down to counting how many pairs of satellites are located on the same side of their host galaxy, like these two, or pairs of satellites on the opposite side of the host galaxy, like satellites 1 and 3 in the diagram here. Our preliminary results, which I have to emphasize still need independent confirmation, are that on average there are more pairs of satellites on the same side of their host as there are on the opposite side. This effect is far and away the strongest for the satellites of host galaxies that are blue in color, where we find 50% more satellites on the same side of their host as on the opposite side. The effect is also present for the satellites of red host galaxies, but it's smaller. There are about 6% more satellites on the same side of their host as there are on the opposite side if the host galaxy is red in color. So what are the implications of our results for the cold dark matter model? At this point, the answer is unclear. What we need to do next is look at high-resolution simulations of CDM universes to see whether or not the effect we see is present in the simulations. What we do know is that previous studies of pairs of large bright galaxies also show lopsided satellite distributions. In the case of pairs of large bright galaxies, the satellites are located preferentially between the two large galaxies, and CDM simulations have indeed been able to reproduce that effect. What I think is safe to say at this point regarding our own study of isolated host galaxies is that it's not a good idea to use the locations of satellite galaxies as a direct indicator of the shapes of the dark matter halos of isolated host galaxies, especially in the case of blue host galaxies. The last slide I'll leave you with shows the contact information for myself and Adam Samuels, as well as a URL you can visit to get copies of images and my PowerPoint slides. Thank you, everybody, and I will turn things over to Lior.
Thank you, Teresa. Hello, everyone. I'm going to talk about one of the most puzzling, maybe one of the most provocative observations, which is the asymmetry of galaxy spin directions. Now, in the next few minutes, I'm going to show about 10 years of work that I've been doing on this observation, but I will focus on two more recent things. The first is that, as weird as it sounds, the asymmetry in galaxy spin direction is coming from the real sky. It's not an error in the instrument, it's not an error in the analysis, it's not foreground contamination, nothing like that. And I'm going to show you some hard evidence to make that case. The second thing is that the asymmetry exhibits patterns. A spiral galaxy is a unique astronomical object in the sense that its visual appearance changes with the perspective of the observer. A galaxy that would seem clockwise from Earth would seem to spin counterclockwise if observed from another point in the universe. But if the universe is homogeneous, the perspective of the observer should not matter. We should see roughly the same number of clockwise and counterclockwise galaxies regardless of where we are in the universe. With digital sky surveys, we have enough data to test it, so we don't need to make assumptions. And in fact, there are some actual previous attempts to test that, but all previous attempts that I'm aware of were based on manual annotation. It means that people manually looked at galaxies and annotated them one by one. But that leads to relatively small data set, and we need large data set to profile the patterns that I will soon show you. But there's even a bigger problem with manual annotation, and that's that there's some systematic bias in the human perception, and that bias is fairly significant. And it makes it difficult to use manual annotation. Here's how I do it. I use computer vision. Now, I will not get into the technical detail of the algorithm. If you're interested, the details are in that paper there. But I will say that the algorithm is not based on machine learning or deep learning or neural networks or anything like that that might have life of its own. I use machine learning for research all the time, but not here. Here, we need something that is model-driven. It needs to be based on defined rules. We need to know exactly how it works, and we need to be able to prove mathematically that it's symmetric. And here's some basic results from SDSS, about 170,000 galaxies. We can see that there's a higher number of clockwise galaxies than counterclockwise galaxies. Now, the difference is not huge, just over 2%. But with that higher number of galaxies, the probability to have such distribution by chance is less than 1 in a million. Now, the question is, which spin direction is more common in the universe? And the answer is an answer we don't always like, but it actually gets more interesting than that because it changes with the direction of the observation. And here we have a rather simple analysis that shows that in different parts of the sky, the sign of the astrometry can change. And we can also see some evidence for agreement between opposite hemisphere, and that is something that I will soon get into. And another piece of the puzzle is the symmetry in brightness. So we can see that in some parts of the sky, clockwise galaxies are on average brighter than counterclockwise galaxies. In other parts of the sky, the counterclockwise galaxies are brighter. And whether we use SDSS or we use Pan-STARRS, we get the same results and we get the same patterns. And even if we annotate the galaxies manually, we still get the same patterns and the same results. So no matter what instruments we're using, no matter how we analyze the data, we always get the same results, and the statistical significance is extremely strong here. And also Hubble Space Telescope shows the same asymmetry, maybe with less data, but that makes it 3 telescopes, and we have no telescope that shows anything different. So at this point, as weird as it seems, this is the universe that we see from Earth. There's no other explanation left. Now, what could be related to the brightness is the change of the asymmetry with the redshift. We can see here that the asymmetry grows with the redshift, such that higher redshift, the magnitude of the asymmetry gets stronger. The direction of the asymmetry does not change, but the magnitude changes. And that shows that the earlier universe was less chaotic than the present universe. Here's an attempt to fit the asymmetry to a dipole. And we do see a dipole here with statistical strength of over 4 sigma, and it shows that there is a pattern to the asymmetry. And because the earlier universe was less chaotic, the pattern is much stronger in higher redshift. We can see that here. And here's an attempt to fit it to quadrupole. A quadrupole has the strongest fitness, over 5 sigma. Now, the blue circle there that you see, that's the location of the CMB cold spot, which is very close to the most likely quadrupole. Now, is it just a coincidence? At this point, yes. At this point, it is just a coincidence. I just thought it was interesting, maybe needs further investigation. And when the signal gets to almost 9 sigma, when the redshift is greater than 0.15, the CMB cold spot is still there. Here's an attempt to fit the asymmetry to octupole alignment. The statistical signal is lower than quadrupole. And here's a comparison between SDSS and Pan-STARRS with 2 different data sets. And now it's never going to be completely identical. We have 2 different data sets, 2 different instruments. There's always a little bit of noise here, but this is as close as you can get. And again, we have 2 completely different systems, completely 2 different sets of galaxies showing exactly the same pattern. And here's my last slide. So there was some analysis of CMB data that shows multiple. I'm sure you've seen those before. The difference is, well, first of all, the strength of the signal, but there's also difference that with spin direction asymmetry, we can compare different redshift ranges, and it's much more difficult to do with CMB. And it's also more resistant to foreground contamination, such as Milky Way obstruction, because it is a relative measurement on the same field. Whatever affects clockwise galaxies will also affect counterclockwise galaxies. CMB is an absolute measurement, so it's more sensitive to foreground contamination. Here's my contact information. I'll be happy to answer questions. And I will leave it to the next speaker. Thank you.
Hello everyone, my name is Sangskriti. I am a graduate student at the Department of Astronomy in The Ohio State University. Today I am very excited to talk about our latest finding on the evidence for a massive hot circumgalactic medium enveloping a large luminous galaxy. We have used the data of 2 extra telescopes, Suzaku and XMM Newton. Our Suzaku result is already published online, and the result from XMM Newton has been accepted for publication both in Astrophysical Journal. Before I tell you the detailed story of our finding, I should emphasize that the 1 million Kelvin hot gas we have discovered is massive and extended, and more importantly, it is the first external luminous galaxy where we have found this evidence. The only other luminous galaxy where we know of this hot and massive gas is our own Milky Way. So our finding is taking the study of this diffuse hot CGM from an galactic to extragalactic level. Usually we think of galaxies as this small disky region where you have the stars and the interstellar medium. However, the CGM, which is the gas surrounding the disk of galaxies, occupies a huge volume around the disk. And we should actually think of the galaxies as this whole volume instead of this small disk. So the term circumgalactic medium is quite literal. It means the gas which surrounds a galaxy. It plays a very important role in the formation and evolution of a galaxy through accretion of gas, feedback of gas, and recycling. The stars and interstellar medium have a much smaller amount of baryonic matter than what you expect for a given amount of dark matter, which means some amount of baryons are actually missing. And as CGM is believed to be a huge reservoir of gas, it might be a potential solution to this problem. I'm saying it is believed because most of the things about CGM are still in theory, and that is why the observational evidences are so important. Now comes our observation. We have used Suzaku and XMM Newton to search for the soft X-ray photons emitted from the hot CGM of a luminous galaxy called NGC 3221. This is an actively star-forming galaxy around 60 million parsecs away from us. In the left, you can see the optical image of the galaxy. The disk of the galaxy is at the center, shown with this bright yellow disk shape. And the region where we search for the hot CGM is between the large and the small yellow circle. As the emission from the CGM is very, very faint, we wanted to make sure that the bright emission from the disk does not contaminate our faint emission, and that is why we remove the small region within this yellow circle. I should also mention that the CGM is dominated by the local emissions, the emission from the CGM of our Milky Way and the solar neighborhood, which are way brighter than the CGM of this faraway galaxy. And that is why the detection is so challenging. In our data, we have two components. One is the signal and the other is the X-ray background or the sky background. Now this background is much, much stronger than the signal. That is why you have to do a very rigorous spectral analysis. Having done that, we extract the faint signal coming from the CGM around the first external luminous galaxy. I should emphasize that this is just an illustration and not an actual image. It just shows that the circumgalactic gas fills up the whole volume where we are searching for the signal, and the emission is brighter closer to the galaxy and it gets fainter as you move away from the galaxy. To illustrate how faint the emission is, here is the spectrum. The red line is the total data and the blue dashed line is the X-ray background. And the little difference between the red and blue line, also highlighted by the vertical yellow strip, is the faint emission coming from the circumgalactic medium. And we have done the same analysis independently using Suzaku and XMM and have found the same emission. That is why we can say with confidence that the emission is real, and this is the first evidence. So that's the first part of the story. We have the detection. And now we go on for the next stage, which is the physical characterization. First of all, the hot CGM extends out to around 200 kiloparsec from the galaxy. For comparison, the disk of the galaxy is only 30 kiloparsecs across, which means the hot CGM occupies 1,000 times larger volume than the disk. And now we go on for other physical properties, for example, temperature. Based on how much mass is there in the stars of the galaxy, you expect the temperature of the hot CGM to be something constant. And outside 100 kiloparsec, we find that the temperature of the hot CGM is constant and also consistent with what you expect. However, within 100 kiloparsec, the temperature continues to increase toward the galaxy. So there is a temperature gradient from 30 to 100 kiloparsec. And also here the temperature is 2 to 3 times higher than what you expect. This temperature gradient and this hotter component have never been observed before in the CGM of any external galaxy ever. It has been predicted by some of the theories, but this is the first observational evidence, which is why it is so exciting. The density of the hot CGM is only 100 atoms per cubic meter. For comparison, I also mentioned the density of supernova remnants, which are millions of atoms in the same volume. And as the emission from some gas depends on its density, such a low density of hot CGM justifies why the emission is so faint and so hard to detect. However, as the volume of the CGM is so huge, it makes up for its low density and gives a decent mass. So the total mass of the hot CGM is 10 billion sun. It is comparable with the mass which is there in the stars in the disk of the galaxy. That makes this hot CGM one of the most massive components in the whole galaxy system. We also find that this mass can account for the missing galactic baryons of this galaxy system. So not only we have the detection of the signal, we have a bunch of interesting information about the galaxy. So here is the summary. So the hot CGM around the galaxies are real. At least we have the evidence around a single galaxy, and future hopefully will be having more. The hot CGM occupies a huge volume compared to the disk of the galaxy. It has a very low density, which makes their emission quite faint. The temperature is not constant throughout the volume. It is higher than what you expect closer to the galaxy, and there is also an evidence of a temperature gradient. The hot CGM is quite massive and can account for the missing galactic baryons. Hopefully by now I have been able to convince you that the CGM is an integral part of the galaxy. So here in AAS you will hear more interesting stories about CGM. And next time remember that CGM should be viewed as something in the galaxy system rather than something around the galaxy. Having said that, I'll stop and take it to the next speaker.
Can you all hear me now? Okay. Hi, everyone. I'm Ripan Saha. Sorry, I was muted. I'm a grad student at the University of Missouri, Kansas City, and we have found a proto-supercluster of galaxies that is 10 billion light years away. So I'll explain these terms in a few minutes. Let me first explain what galaxy clusters are. Galaxy clusters are the most massive gravitationally bound structures, up to 1 million billion times the mass of the sun. Galaxy clusters started forming 12 billion years ago when the universe was very, very young. Smaller groups of galaxies, gas, and dark matter come together to form galaxy cluster. In the process of formation of these galaxy clusters, an intercluster medium of hot gas is also created. On the right, you are seeing a beautiful picture of a massive and distant galaxy cluster where you can see lots of galaxies in it and also hot gas in the center of the galaxy as seen by the Chandra X-ray observatories. On the other hand, galaxy protoclusters are the ancestor of galaxy clusters. They're much extended structure where the galaxies live in a much larger space and will eventually collapse into galaxy clusters by today. Unlike galaxy clusters, protoclusters usually do not have hot gas in them. I've shown 4 different examples of galaxy protoclusters where the red color represents the most overdense region of the galaxies in the protoclusters. This is the current status of the galaxy cluster and protocluster surveys. This is today, and this is the time when Big Bang happened. So the x-axis is basically representing a timeline. It is also telling us how far these galaxy clusters and protoclusters are from us. As you can see, there are many surveys like the X-ray surveys and radio surveys done by Planck and South Pole Telescope has already found lots of galaxy clusters. Majority of these galaxy clusters are in the nearby universe. A handful of them has been found in the distant universe. Different other techniques adopted by different other surveys has found lots of protoclusters in the very distant universe. If you have looked closely, you'll see that there is an era where not many galaxy clusters or protoclusters have been found till date. But this era or this time is very, very crucial because this is the time when galaxy protoclusters collapse and become galaxy cluster. The IDCS cluster that I've just showed in my previous slide is basically one of the rare galaxy clusters from this era. This galaxy cluster is located 10 billion light years away from us, and in redshift term, this is at redshift 1.75. We need to find more galaxy clusters like this so that we can understand the evolutionary connection between these galaxy protoclusters and galaxy clusters. How galaxy protoclusters transforms into galaxy clusters is an interesting open question that we can answer if we have a large sample of galaxies, clusters, and protoclusters from this era. In this work, we are reporting a new method of finding galaxy clusters and protoclusters using a signpost called dust-obscured galaxies. Dust-obscured galaxies, or popularly known as DOGs, are optically very faint galaxies, and it can only be seen in infrared surveys. Generally, dust-obscured galaxies have lots of ongoing star formation in them, or they host a supermassive black hole which is very active in their core. And most importantly, these DOGs live in an era or are observed in an era where we want to find galaxy clusters and protoclusters. In parallel, many studies done in the last decade has also found that galaxy clusters and protoclusters in this era have large number of star-forming galaxies and supermassive black holes in their core region. Based on, motivated by these studies, we want to verify whether we can use these DOGs as a signpost to find galaxy clusters and protoclusters in this era, which means if we observe a DOG in this era, we would want to verify, is there a nearby galaxy cluster or protocluster? We have developed a pipeline and applied that pipeline 10 billion light years away to find galaxy clusters and protoclusters. And we have got some interesting results. The first thing I want to show, this is a galaxy cluster candidate that we found using this DOG, which is represented by this green circle. And this is a galaxy cluster which has been found by our pipeline. And our pipeline also found the same structure using another DOG, which is located here. So our pipeline has decided, has the capability of deciding whether this is an actual galaxy cluster or not. And it ultimately found that this galaxy cluster candidate has been signposted by these two DOGs. Here's another galaxy cluster of normal galaxies, where the normal galaxies are located 10 billion light years away and are denoted by these yellow boxes, are also signposted by two different DOGs here and here. And the interesting thing about this cluster candidate is that it also hosts a radio galaxy denoted by this cyan circle, which is kind of at the center of this galaxy cluster. The importance of having a radio galaxy, finding a radio galaxy in the center of a galaxy cluster, is that most of the galaxy cluster have a central galaxy which is very active in radio wavelengths. So this result kind of confirms that statement. Here's another cool, interesting story about our result from our analysis. We have rediscovered the IDCS cluster that I've just showed in my previous slides. We have rediscovered this IDCS cluster totally independently using our DOG signpost method. This IDCS cluster was discovered 10 years ago by a different method, but now we can discover this massive cluster using our DOG signpost method. This is the most interesting result from our analysis. We not only have identified lots of galaxy clusters using our DOG signpost method, but we have also discovered that these galaxy clusters are part of a bigger supercluster or network of galaxy clusters. And all of these galaxy clusters are located 10 billion light years away. Here, by the black box, I am representing the location of the IDCS cluster, which is the most massive clusters ever found at that distance. And all other white circles and yellow circles representing detection of new galaxy clusters using our DOG signpost method. If you look closely, then you'll see that there are darkest blue regions and light blue regions. Dark blue regions represent basically the most dense part in the sky, where the density of the galaxies are maximum, and the light blue regions are representing where the galaxy density is low. So if you track these circles, you'll see that these clusters is like node in a filamentary structures and connected by low density regions or filaments. So this supercluster is interesting not only because we found it at a far distance, like 10 billion light years away. This is also interesting because there is a massive mature cluster already found 10 years ago in this supercluster. it's like there is a massive cluster in this network of cluster, and it is surrounded by lots of other clusters, lots of other nodes that have already been formed or in the process of formation. The stars you see here are basically the galaxies in this supercluster for which we know the distances very precisely. And the green circles are representing the dogs that we have used as a signpost to find these galaxy clusters. So finding this supercluster is like visualizing two things simultaneously. One, a very massive galaxy cluster, and it is surrounded by lots of other clusters that are in very nascent stage. It is like visualizing a mature cluster in its surrounding birth structure. People have found superclusters at further distances or at closer distances, but this is very interesting because this is the first time an observational confirmation of a massive galaxy cluster, which is still embedded in its birth environment. Here's the summary. We have verified that we can use dust-obscured galaxies to trace large scale structures like galaxy clusters and protoclusters at a very high distance. We have recovered known galaxy clusters using our signpost method, which 10 billion light years away, and we have found that these massive clusters are still embedded in a network of galaxy clusters or in a supercluster. And if we continue multi-wavelength studies of the supercluster, we'll be able to understand how these protoclusters transformed into galaxy clusters at such high redshift. Thank you very much.
Thank you very much. So everybody can come back, audio and video. Well, I will call that a smashing success. Everybody kept to time and we didn't suffer any serious technical issues. So Lior, you can come back if you wish. Susanna as well, if you wish. So
okay.
What's interesting here is that because the Q&A is handled by the text chat, after each speaker finished their presentation, they started answering questions. And so a lot of the questions that have been asked have already been answered. At the moment, we have 3 open questions. And so I suppose we should answer those live since we're all back and we have the time. So if each of the speakers, if all the speakers could unmute and also make sure you're looking at the Q&A box. It looks like we have, let's see, we have a question from Leah Crane, new scientist, I think, if I'm not mistaken, asking Lior if you can clarify what rotating with respect to itself means in terms of the rotation of the universe.
Okay. Yes. So, well, first of all, the rotation explanation, that's one interpretation of the observation. That's of the spin, whether the universe was born spin. That's one interpretation. It's not necessarily there will be, and there are already some other interpretations to that. So I don't want to make a definite statement about that thing. There could be other interpretation to that, and yeah, that's a tricky thing here. Whether if the universe was born spinning, yeah, it would be that, for instance, the building blocks, the galaxies around it would actually, that's something that if the universe was born spinning, we expect also spinning galaxies, spiral galaxies, to be much older than they are based on other models. If I said it last year, then you'd think I was crazy, but now we see that those galaxies were actually, galaxies actually exist. They were detected. So there are some evidence that fit into that. And I hope that answers some of the question. I don't have a complete answer to that question. Again, it's just one interpretation of it. There need to be more work. There need to be more work on that.
Can you just mention one or two of the other possibilities besides the universe spinning, just so we can have a sense of, you know, what the other possibilities might be?
Yeah, well, the other possibilities were not proposed by me. I saw some other work done in the short time after I put this thing on Archive. I saw one explanation that is by partly breaking gravitational waves, something that gravitational waves that I carried from the early universe and exhibit themselves through the asymmetry in spin directions. I haven't gotten yet very deep into that explanation. Again, it's not an explanation that was done by me, but there are other things that don't might not require the violation of the foundational assumptions.
So some other scientists have seen the data the way you've presented it, and there are a number of explanations in circulation.
Right.
So they're not just dismissing the data as, you know, somehow faulty.
No, the data at this point, again, my claim is that I don't claim that there's no error in this. I claim that there's no possible error that could exhibit itself in that way. You have several different telescopes showing exactly the same thing. You have several different analysis methods showing the same thing. And the pattern is not a pattern that would be, that could be the result of an error, because of the pattern is so, is clear. The clear pattern. It's not like a noise that you get from somewhere, or a bias, a systematic bias. When you get the different thing in opposite hemispheres, that we have agreement between opposite hemispheres and things like that. That can't be an error, and you keep getting the agreements between opposite hemispheres when you measure the magnitude of the brightness of the galaxies, when you measure the population of galaxies. You keep getting them regardless of what instrument you use, regardless of how you analyze the data. So there's so many things that work together here, and that's at this point I don't think we can. Again, it's not work that I've been doing this year. It's about 10 years of work, and the evidence just accumulated over those 10 years. Yeah, but there are other explanations that don't require the violation of the foundational assumptions. But again, these are not my explanation, and I haven't yet gotten deep into those explanations.
Okay. There's been some discussion in the Q&A box. Everybody should be able to see, all the attendees should be able to see the questions that have been asked and that have been answered by one of the presenters by typing their answer. So if you could scroll up and down through the Q&A box, you'll see all the questions that have been asked and answered so far. I'm trying to see, it looks like we don't have any other questions that haven't been answered yet. I have a few questions myself. I can't be paying attention to the technical aspects of this, and also, well, actually, I can't, as a panelist, I can't type questions into the Q&A box anyway. Let me see if I have any questions here that haven't been answered yet. As far as I know, I think for Shamskriti, I was curious how you chose this particular galaxy as your target. Did you have some reason to suspect that it would be a good candidate for finding a hot circumgalactic medium, or was there just something about the available data from Chandra and XMM? Just curious how you managed to get lucky with this one, or whether you looked at a bunch of galaxies and this is the only one for which you found the hot CGM.
So it's a very good question, because the target selection happens to be a very important part of this hot CGM search. So the thing is, the signal we are searching for is very weak, and it is dominated by the background. Usually we find that the signal is only 1% of the data. So you have to make sure that your background estimation is, optimum. So one of the things is that you need to estimate your background and your signal from the same observation. And that you can do only if the galaxy is far enough, because otherwise, if your galaxy is too close, for example, if the galaxy is say 20 kiloparsec away, the field of view of XMM Newton will go out to say roughly 50 kiloparsec. That means it's just the signal, and it is very hard to estimate the background from that. So we wanted to choose a galaxy at a distance of at least greater than 55 kiloparsec, and this one is a 55 megaparsec, and this one is at 60 megaparsec. So that's why distance was one of the things. And also we are searching for Milky Way like galaxies, so you already constrain the stellar mass. We wanted to search for hot CGM around star-forming galaxies, so that we are more likely to find the CGM, because some people think that stellar feedback is one of the important things which is driving the hot CGM. And this galaxy has a star formation rate of 10 solar mass per year, which is pretty large. So that makes it a very good candidate. And the reason for choosing Suzaku and XMM for our analysis is that both of them have pretty large field of view, so that you can sample a pretty large region within your field of view. When you're searching for an extended medium, that is very important. So.
Okay, and another question for you. You mentioned that this hot circumgalactic medium can account for the what had been previously missing baryons. There was an interesting paper that got a fair amount of publicity a few weeks ago about using fast radio bursts and their propagation through the intergalactic medium to determine that they apparently found the missing baryons that way too. So I'm wondering if you've had an opportunity to check whether your data are consistent with that result, or if there's any reason to wonder whether you're looking at different populations of baryons.
So I would say these two studies are not directly comparable, because what they are searching for is the missing baryons in the intergalactic medium. So that's more of a cosmological problem. So you compare the baryons in the intergalactic medium and see if it is, consistent with the cosmic ratio with the dark matter. But what we are searching for is missing galactic baryons. So in this case, we are just confined within the dark matter halo of the galaxy only.
Okay.
And we are trying to understand whether the galaxy is baryon sufficient, I would say. So it doesn't directly translate to the amount of baryon in the intergalactic medium. I would say they're complementary, but not exactly comparable.
Okay, but they've found missing baryons in the galaxies, and you're finding them in the galaxies. They're finding them in the intergalactic medium.
Yes.
But in any case, they're not missing anymore.
Well, we have only one galaxy, and we need to do this for many, many galaxies to claim it with high confidence. Yeah. But this is an important first step, I would say.
Okay, great. I also have a question for Ripon Saha. You're looking at galaxies and clusters of galaxies so very far away that presumably, well, my question is, how do you distinguish when you can't really resolve galaxies too much in terms of shapes and sizes and all that? How do you determine the difference between something that you're calling a protocluster and something that might be described as a more mature cluster? What are the discriminants? What are the criteria that you're using to decide, one versus the other? Is it just how far away they are, just their apparent age, or are there other characteristics of the galaxies or the cluster itself?
The most important factor in deciding whether it's a protocluster or a cluster is of course, the redshift one. And number two is the size, the extent, the physical extent of the structure. A galaxy cluster has a physical size of like 1 megaparsec or 1.5 megaparsec at those redshifts. But protoclusters at those redshifts spread out to a much bigger area than 1 megaparsec. Protoclusters at 1.75 can have a physical size of 4 to 5 or 6 megaparsecs. And so this is the most important thing in deciding whether it's a protocluster or a galaxy cluster. And if you have extra observation, and then you can confirm the difference between a protocluster and cluster, because as I said in my talk, that galaxy clusters have a hot ICM, or intercluster medium of hot gas, which protoclusters do not have. So if you observe the galaxy cluster using X-ray telescopes, you should see an ICM. Whether if you observe a protocluster, you should see nothing.
Okay, it looks like there's a question for you, or for Lior from Govert Schilling. Do you see that question, Lior? If so, you can answer that live.
I cannot. Where is that?
It's at the very bottom of the open Q&A.
Oh,
You see it?
oh yeah. That was right. So that was, because I'm not entirely sure what the question refers, but I think it was about 6 months ago. The alignment of galaxies. Yes, so that was a study with a smaller set, a much smaller set of galaxies that they, as far as again, I'm talking about someone else's research now, they found out that galaxies are way too far from each other to have gravitational interaction, actually have alignment in their spin direction. And they did not provide a proven explanation of that, but they made that observation about 6 months, and that observation is aligned with a lot of the work that I've done. So it's not just my data showing. So that's another indication that another evidence to show that there is some alignment between galaxy spin. There are some patterns there, although the galaxies are way too far from each other to have any gravitational interaction. And as a general comment, I'll say, yeah, it's that, and that was also a surprising result. But every time we think that we figure out the universe comes back to us and shows just some humility. So we think we know about the universe and what can happen and what cannot happen, and then it happens in the past so many times that we got that wrong. So the universe is full of surprises. Yeah.
Okay, another question just came in for you as well from Robert Nemiroff from Astronomy Picture of the Day. Do you see that one? Could you comment on whether relativistic beaming plays any part in your signal?
Relativistic beaming. Okay, yeah. So yeah, that's a good question. So yeah, relativistic beaming is one explanation of why clockwise galaxy would have different brightness than counterclockwise. Let's say the Milky Way rotates, and the galaxies that we observe also rotate. A galaxy that rotates in the same direction as the Milky Way will have different relative rotational velocity compared to the same galaxy that rotates the opposite way. And that can lead to, it's true that it can lead to some brightness differences. And I did look into that. I did do the numbers. When you plug in the numbers, then the maximum brightness asymmetry that you expect is a 0.009 magnitude. And with the galaxies that we have, we already observed 0.05 magnitude difference, and that's probably not even the maximum. So for that to be explained by relativistic beaming, galaxy needs to rotate at least 10 times faster than they actually do to explain it by that. And so according to the physics that we have now about galaxy rotation, the physics that we have right now doesn't explain. Maybe if there's like dark velocity or things like that, I don't know. But the physics that we have right now doesn't explain that. And the other thing is that I did compare the absolute magnitude of galaxies. And the absolute magnitude, you don't have a symmetry. in the apparent magnitude, you have a symmetry, and in the redshift, you have a symmetry, but in the absolute magnitude, the symmetry is gone. And that's another indication that it's probably not, it doesn't look like it's relativistic beaming, but it's but right, that's one of the possible explanations, but I did a lot of work in the past to look into that, yeah.
Okay, very interesting. All right, well, I don't see any more open questions. If anybody else out there among the attendees wants to ask a question, this is sort of your last opportunity. So please feel free to type in one more. Otherwise, I don't have any more. Does anyone have a question for any of their fellow panelists? All right. Well, then I think we'll draw this briefing to a close. I want to thank all of our panelists. I want to thank their public information officers who helped us all prepare for this briefing. And as I said, I think there's at least one more press release coming. I have to go back and check and see what I've got queued up. But I appreciate all of the help that each of the institutions that you guys work for have provided. The next briefing will be at 3 p.m. Eastern time this afternoon. The title of that one is Cosmic Bangs and Whimpers, about explosions of various intensities. And I think with that, I want to also thank Tharani and Susanna for your help keeping things going this morning. And I think we'll call it a morning. Thank you all very much.